Good morning, Dr. Indah.
Good morning, Dr. Anna.
Okay, thank you for joining this lecture.
Okay.
Sensei, now 8 o'clock in my country and 10 o'clock in Japan. Let's we start lecture. Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good morning, everyone. Thank you for coming this lecture. Also, thank you, Professor Izumi, and then Dr. Indah Primadona as a speaker for today agenda. I think today the last event lecture from Professor Izumi, the first program at the Tuesday workshop preparation how to write the paper, and then yesterday program guest lecture, and then today I think the last program workshop characterization of material. Before Professor Izumi start for the lecture, I would introduce again. Maybe some of my students here not come in the yesterday or the yesterday before lecture. I want to share again curriculum vitae of Professor Izumi and also Dr. Indah Primadona. Wait a moment. Yes. First speaker is Professor Yasuo Izumi. Date of birth January 4, 1965 in Tokyo, and then finished Doctor of Science, the University of Tokyo. Experience research in about Stanford University, California at 1996 until 1997. Field of study, Professor Izumi, surface chemistry, environmental chemistry, and also X-ray spectroscopy. Izumi Sensei graduate bachelor from the Sem University of Tokyo, also master degrees, and then finally completely doctor course from University of Tokyo also. For the job, Professor Izumi when 1989 Asahi Chemical Suzuka Factory, and then research associate in Tokyo Institute of Technology, and then go to Stanford University by Monbuso Scholarship at June 1996, and then after that come back to Chiba University as associate professor in July 2007, and finally got the professor at April 2018 at Chiba University. Now, until now, Professor Izumi is the professor at the Department of Chemistry, Graduate School of Science, Chiba University. And then for committee, societies, and activities, also many Professor Izumi, like editorial member, the Surface Science Society of Japan, also reviewer, Petroleum Research Fund, Washington, USA, and then also member American Society of Chemistry, this one, and then many member and activities Professor Izumi until now. This one society member number American Chemical Society, and then also Catalysis Society of Japan, and then American Society for the Advance of Science. Okay, let's next the prize. Professor Izumi also got some prizes. July 2000 Young Scientist Prize, and then in March 2001 Fujino Prize 2000 of Tejima Foundation Award, and then other prize. Okay, let's now we go to original paper. I think this one is selected paper as published Professor Izumi and the member of the lab almost 1905, maybe more than 95 until now. This is about catalytic and photocatalytic, and also preparation cluster metal oxide, and also many topic has published from lab Professor Izumi. And then we go to another slide. Also, Professor Izumi has published some books. Again, I want to introduce that Professor Izumi published a book with my professor when I got the doctor program in Osaka Prefecture University. My supervisor is Professor Anko. Together with Izumi Sensei has published 2 books about photocatalytic. Let's I saw one moment. Okay, this one. Yes. Number 4. This is my supervisor when I got the PhD program in Osaka Prefecture University. Professor Izumi also published book with my Professor Anko, and then this one also my professor. And then the last but not least, this is Professor Izumi now as a reviewer also, and then also many activity until now. I think enough for Professor Izumi. Now I go to Dr. Indah. Dr. Indah, this is my friend, my best friend. Professor Indah from Pajajaran University for bachelor, and then master degree from National Taiwan University, and then got the PhD from National Tsinghua University, also in Taiwan. Now he is work in Research Center for Chemistry, National Research and Innovation. This from government, our government, maybe in Japan, this name Rikeng. Yes, Rikeng mean in Indonesia, before we name LIPI, now change to BRIN. BRIN same with Rikeng in Japan. Dr. Indah, chemistry, pharmacy, and then chemistry. This is also only selected paper, recent advance and rational design strategies of carbon. Also, Dr. Indah concerned in photocatalytic activity. Similar with Professor Izumi, also same topic with me. Also now Dr. Indah also collaborator Pajajaran University, and then Dr. Indah also as the team teaching for undergraduate lecture in Pajajaran University. I think enough to introduce Professor Izumi and Dr. Indah. Now I think the first speaker, I invite Professor Izumi for the first. Sensei.
Mm-hmm.
Yes, please. Now screen is yours.
Okay. Maybe date is not. No, this is not today. Sorry. This is not. Wait. No. Okay.
Yes, please.
So today, world-class professor program organized by Diana-san. For me, today is the third part of this lecture, characterization of materials. But as the program of the Diana-san, yesterday was for student, Diana-san student. So this is second part of the Diana-san lecture. So from very general thing. So so analysis, characterization. So this is very, very general thing. So how analyze materials? So possibly materials would be solid, maybe immersed in liquid, but or maybe solid in contact with gas to promote reaction at surface. So these are very, very basic drawing of the methods we perform for the characterization. So electromagnetic wave, such as the X-ray or UV light, or even visible light, or maybe infrared, is irradiate sample and see transmission, or this is sample. The pink is sample, and the electromagnetic wave is the arrow. And this is transmitted electromagnetic wave on right-hand side. This is absorption. Like FTIR is something like this phenomena. Or electromagnetic waves comes to your sample and the direction changes. Electromagnetic wave direction changes. If that comes down, it's scattered upward or diffracted upward, like your X-ray diffraction or scattering, some UV scattering, these phenomena. But you can also use electrons for your characterization of your sample. So electron, similarly to electromagnetic wave, electron is not electromagnetic wave. The electron is, in quantum mechanics, its electron appears. And electron basically behave like particle. Possibly it also behave like wave, but if I explain its behave like particle, very, very small particle that I cannot see it. The electron, for your sample, it's transmit, maybe partially absorb, but this is something like your electron microscope. You insert a plate sample in your apparatus and measure transmitted electron. And the very detailed structure of the transparent sample structure is visualized. And electron, similarly to electromagnetic wave, electron scatter to your sample or diffract. So in this context, we would call this wave or electromagnetic wave or electron as probe, because we try to see your sample information using probe. So probe is not necessarily be electromagnetic wave or electrons. You can use ions, like what ion? Argon ions, whatever. The atom ions can be used for, and maybe ions. I do not think it transmit to your sample. Ion maybe trapped in your sample. So when you use ions, scattering or diffraction, diffracted ion or scattered ion is used, monitored to analysis. So this is too much, maybe too much the fundamental, but to think about the characterization, and I think the scope of the interest varies for today's audience, not students. So everyone has each research topic and research interest. So I think I'm always to talk from the beginning, I think, because scope is wider today, I think. So electromagnetic wave, this is the classification depending on the wavelengths. So gamma ray is the shortest wavelength. So 0.1 nanometer, you may call this 1 angstrom, I do not know. Maybe often use nanometer, I think, these days. So less than 0.1 nanometer, so shorter than hydrogen-hydrogen bond length. So this is maybe somewhat shorter for chemistry, because chemistry for today's topic, bond chemical between atom bond is the very important topic to also for today's characterization. So, but gamma ray may be used also. So then 100 to 0.0 nanometer, this is most of, maybe I would say most of our interest. It is within the metric length region, the X-ray. So I'm performing the many studies using X-ray. So today's talk would, 1/3 of today's talk maybe using X-ray. So, but like yesterday, the question and comments, the infrared question was, infrared ray question was raised. So infrared, but between X-ray and infrared, of course, visible light. Visible light is 700 or maybe 800 to 400 nanometer, depending on your eye, the eye color, I think. So for me, maybe 800 to 400. And 400 to 200 nanometer, this is UV light, ultra visible ray, and 200 to around 300 UVC. 300 to 400 is UVB, UVC, depending on the effect on your skin or on your. But this is today's topic. This is in sunlight, the UV light is not the major component. This is 3 or 4%. 1% was often saying about this. The 400 to 200 nanometer. Actually, it is very critical, the wavelengths for our application. This is, and today's analysis, characterization corresponding to your application using, for example, 400 to 200 nanometer UV light, the characterization is also performed using this light. This is something application and also probe. And visible light, near infrared and infrared centimeter inverses. So you need to convert the units, make this nanometer. So 10 power 7 and inverse, centimeter inverse is often used like this. Here it's not written, I forgot to write. And microwave and radio wave. But this is centimeter length, so more like our general life, daily life, what we can directly see length. So today's topic, so then classification as I showed before, electromagnetic wave, depending on these wavelengths, transmission, so mass power or umlaut. FTIR, exhaust means, X-ray absorption spectroscopy. So mass power is gamma ray. FTIR is infrared ray. Maybe also you see near infrared ray. And exhaust is X-ray. UV visible is your apparatus, the ultraviolet and visible. Possibly two lamps is equipped inside your apparatus, and possibly also including near infrared lamp also. And nuclear magnetic resonance is the other. This one. So NMR is also used. And for scattering and diffraction, So Raman is the Raman is, I think, the infrared. And X-ray diffraction abbreviation is written here, but X-ray diffraction may be familiar for the field in material characterization field. Researcher person, audience, it's very, very familiar, the X-ray diffraction. Using X-ray in this region. X-ray diffraction, copper K alpha. Copper K alpha is the 8,000 electron volts X-ray. So one of the energy within this region is fixed energy, fixed wavelengths. Light is used. And also diffuse reflectance is, this is not transmission or scattering diffraction. I think already these lectures I heard sometimes, I think the diffuse reflectance is the diffuse reflectance UV visible or diffuse reflectance infrared. Yesterday's comment was the infrared using ATR, the diamond, such the applied the technique is also used and many person is using. So to understand this difference or the advantage of this technique is essential to choose, because operators in many facility and country facility and in many laboratory, these equipments is available, but to choose the best and possibly, if needed, to prepare your own reactor or reaction cell is maybe needed to characterize directly or to monitor directly what happens for your sample or for your sample or for your designed chemistry laboratory, small laboratory in your reaction cell. So, and methods, this is continued an electron beam. Electron is, it just depends on how the electron speed. So how that is accelerated using the electrodes, I think. It depends, so it's characterized depending on the electron speed, but electron transmission is TM. TM is transmission, absorption, transmission, electron microscope, and HR is high resolution. High resolution means this is, I think, today I've not prepared, but all our recent paper, it includes high resolution TEM image to show the crystal structure included in our sample. It's very, very fundamental to show in our, for example, composite photocatalyst, what kind of crystal is included, and the size is very, very critical, because on the surface of the crystal, photocatalysis takes place. Reaction itself takes place, and the photocatalysis also inside the materials, composite materials, check about that, and inside electron and hole is created. So crystal structure is essential. And also this is the relatively long name. This is the, I don't, this is, angular diffracted fields, dark fields, angular, something like that. So this is the detector is different. So, and making different detectors compared to the normal TM and dark field image is followed in this scanning transmission electron microscope. This is the to identify in this TEM, new type of TEM, but becoming maybe familiar. Everyone try to show this hardest STEM image to identify your elements. So elements, it focus on the brightness of your sample depending on your element. So element atomic weight square. Normally so brightness is dependent on the number of electrons. So for example, for your cobalt sample, 27 electron, if cobalt is neutral. And for example, for your aluminum sample, 13 electron is included. So brightness is somewhat different. But if you use hard STEM, the image of cobalt is 27 squared power 2, not square, power 2. And aluminum brightness, aluminum atom, if this has atomic and as metal, the brightness is 13 power 2. So the difference becomes much greater. And you can identify, for example, the cobalt nanoparticle existing among the sample. It's more brighter using this. So by comparing these two, often you characterize. So this is using electron as probe, and transmission is monitored. So for this purpose, you need to make your sample as thin as possible, because electron may not transmit the sample, you see nothing. And so instead, or maybe for different purpose, I think most of the people, for different purpose, SEM, so scattered electron microscope is also measured, not for high resolution way. The scattering secondary electron is monitored to see your crystal shape. I think I do not know explanation. I think most of the audience know better than myself. But associated with these techniques, electron probe microanalysis. So you analyze the X-ray. When here it's simplified picture. So electron and something is coming out. So it's not necessarily electron. Electron is beam is injected into your sample, maybe into your sample surface, because electron may not penetrate so much. So, but you also, your sample also ejects electron. So, electron as well as X-ray. So X-ray is analyzed for electron, and electron, the making your electron speed rate is slowed down. The diffraction, or in different setting, the R heat is also met. So, and then the classification, the last classification as the ion beam as a probe, the SIMS, this was the scattered ion scattered ion micro. So SIMS measures ion scattering, and ion is monitored by the ion detector, mass spectrometer. It's monitored, and to see the surface characterization is done. Ion penetrates the minimum length of surface, so its size is much bigger than just electron, one electron. So much bigger. It includes the not so nuclear also as well as the electrons. So much bigger. So you see surface characterization. So these are just the order. It may not be very good. Here. Today's talk is 1 hour, but maybe 1 hour maybe to talk everything about characterization. Also, yesterday's talk to talk everything for characterization may be difficult. So I need to choose my topic from our laboratory, maybe shown as the example, and hold the lecture of characterization materials needs the lecture for students, like the two months lecture or 4 months lecture may be needed. So today I limit this the topic from our laboratory, and this is not connected well. Also yeah. So to analysis probe and spectroscopy was shown. Actually, diffraction is not spectroscopy, but so characterization. Maybe this is not characterization, but maybe people in analytical chemistry you would say characterization. But I also explain as characterization, or maybe this is the monitoring of your photocatalysis or catalysis reaction. But you may say the analysis of your gas sample or in your liquid synthesized sample in organic chemistry. So mass spectrometry is also taught. So mass spectrometry is this is not spectroscopy, but maybe you would say spectroscopy because it's differentiate the weight of mass divided by the charge. So mass spectrometry is so mass spectrometry is used to monitor this reaction, time course reaction. This is for the catalyst. Part of the talk was done. So this is continued from yesterday's talk. So sorry for the somewhat the complicated structure of my talk, but it's connected from yesterday's talk. And so it's not directly connected to electromagnetic and electron probed spectroscopy talk, but I try to introduce the mass spectrometry also for the characterization. So 13 CO2 gas was analyzed here, and 12 CO2 gas was analyzed also. So for this analysis, mass spectrometry is used. This is one of the technique, and this type of the detector, positive, negative. It's written somewhere, and the electron field is some very complex. So this is molar weight, and Zm is molar weight of your molecule, exactly saying ion formed from your molecule. Because electron hit to your sample, I know it. Here, your sample comes in here, and this is maybe here. So this is ionization section. So electron is injected to your sample, possibly to your gas sample. So for example, your CO2 is oxidized, the electron hit, and the possibly one electron in your CO2 molecule is disappear. So CO2 plus is formed. So plus means the charge is +1. So G is 1. So M is 12, 16, so 44. So divided by 1, so 44 number is detected by the electric field formed with this 4 further pole, and your sample is detected at this detector by these 2 electron field, U plus D, and the field, the electromagnetic field is modulating with this time function, the cosine omega t, and then you can distinguish the 13 CO2 plus 44 and 12 CO2 44 and 13 CO2 45 is distinguished up here. So this is mass spectrometry. So mass spectrometry is also used, but also for these operators, it's for us, our application, it's very helpful because the mass spectrometry is connected to gas chromatograph. So gas chromatograph, they distinguish CO2 because we also have products in this. This is just the exchange reaction in time course, but product CO, methane, ethylene, propylene, ethane, propane, these products need to be distinguished. So mass spectrometry is sometimes confusing because here CO2, I said CO2 is oxidized. So CO2 plus 1 is detected as the 12 CO2 plus 44 and 13 CO2 45. But what is complicating is your CO2 also dissociates partially. So CO is detected also in your mass spectrometry analysis. So you see 28, 12 CO. It's not product, it's confusing. In your mass spectroscopy, the detector, you have CO. It's dissociation. It's not photocatalytic product. In your mass spectrometry derived CO. So 28, 12 CO and 29, 13 CO is detected in your mass spectrometry detector reaction. So to avoid this confusion, the solution is simple. You connect mass spectrometry directly to gas chromatograph. Gas chromatograph, basically, in principle, it differentiates all the type of gas. So methane, CO, CO2, hydrogen, propane, propylene, ethane, ethylene, these products is differentiate. Methanol, ethanol. So basically, I introduce the technique for characterization, and I go into the chemical, the analysis set part. So maybe but I still have time. Yes. So this is exchange reaction, continuing from yesterday's talk. So for time is x-axis, and this is amount of the gas. So 13 CO2 gas was introduced, and it drops quickly because it adsorbs on our zirconia sample. And at the same time, the 12 CO2 evolved, and these 2 type of gas, both are CO2, but the isotope labels differentiated and reach equilibrium, both zirconia and AG silver zirconia cases. And the content of the 12 CO2 was, this is about 3 among 55. So 9.3% CO2 was 12 CO2, although our reagent 13 CO2 contained 99% 13 CO2. So surface adsorbed 12 CO2 was detected by this fundamental exchange reaction test. So this CO2 adsorbs strongly on zirconia surface. this was found using mass spectrometry. And so question, if student is also attending this lecture today, please solve this question. This is the adsorption step reaction constant, assuming one order, first order reaction. And this is desorption reaction constant Kr prime for CO2, adsorption, desorption. And your CO2 pressure is, please solve the equation and obtain this reaction. So using possibly your Atkins textbook. I'm teaching for the first year student for this topic. And then as the classification of the electromagnetic wave, this is the 200 to 400 nanometers. So this is UV range in the figure, and spectrum is also drawn here, depending on our silver zirconium dioxide sample. And between 400 to 800 nanometer, this is visible light range. So purple, green, red, orange, yellow, green, or something like that. So here it's like absorption is measured depending on the amount of silver in our sample. It becomes progressively greater and reach maybe constant around 10% silver amount in our sample. And so this is characterization, and this is fundamentally this rising edge exists at 248 nanometer here. So this is zirconium dioxide absorption, steep absorption. So this is the semiconductor characteristics based on characterization technique, this UV visible technique. And this is our catalyst is powder. So we cannot measure this kind of the good data, but in transmission setup, it becomes much more noisy data is obtained if I try to do in transmission setup. So diffuse reflectance, I added the one, sometimes it's written DR methods. So diffuse reflectance setup is used to this is the two person to consider the transformation of the diffuse reflectance yields into absorption like yield, theoretically. So these two-person Kuberka-Munkh equation, this is transmission absorption like data based on theory. And here, so this is the semiconductor light absorption, UV light absorption, UVC light in this case. So semiconductor has the steep absorption. So semiconductor is like has certain band splitting exists for semiconductor. This is called band gap. So electron is filled at the valence. Valence is the electron valence, like valence bond. The electron is filled at the valence band, and here conduction band. So it's between the band, the electron is not filled. So this is the band gap absorption, and here this is the localized surface plasma resonance. So this sample is color was yellow. So by this absorption, color become absorption of the violet color, the sample color appears differently, and this is surface on silver surface, silver nanoparticle 3 nanometer silver sample sample. So the nanoparticle based on, maybe I have 10 or 12 minutes to talk. The silver nanoparticle, the surface, at the surface, electron is excited as group, and this peak appears. And depending on the size of silver, the top position slightly changes. So this kind of characterization can be done. The associated with the electron microscope, hopefully high resolution transmission electron microscope, and hard STEM to visualize, to clarify which is silver nanoparticle, because zirconium dioxide is relatively heavier elements, so zirconium. So we need to distinguish these two elements. So this resonance is so you're partially UV, but also as the visible light absorption, it's related to photocatalysis for this catalyst, CO2. And X-ray, so the apparatus. So, and I said, I think in textbook, I think most of the audience know today what I'm talking. And so something in addition for your information, maybe the laboratory made the cell, or laboratory made the what to say that apparatus or reactor or online connection. These are, I think, somewhat hint for your further success in your research, your own research. So I might try to utilize more of this apparatus. This is so mass spectral. Sorry for this is the real side. Because to show everything, I only have this angle. So, and this is mass spectrometry, and this is gas chromatograph, and connected directly here. It's by tube inside, and this is the reactor, and photocatalysis is not shown here, but here it exists, and this is sampling section. So photocatalysis is performed by setting light below of this left side below the photocatalyst, our photocatalyst, and UV visible lamp is set and performed, and it's inside this the Pyrex glass system. Reaction takes place, and reaction gas and also circulates, and this is sampling section, and here it's connected to this white, this line is helium is coming from here. Origin is here. Helium tank is here. Now it's becoming much more expensive. The helium is United States, but helium is United States, but maybe to ship, maybe it costs more, or I do not know. So it costs, but we purchase, and helium comes here and sampled here and go here and come back. And this is heated at 120 centigrade because water may be absorbed here and stuck. So, or methanol is maybe stuck inside. So we heat always at 120 centigrade. So such fabrication may be helpful for your further study if you have something extra is needed for your study. So, and this is X-ray absorption section, but for not to interfere, next speaker, I try to finish in 1 hour my talk. And this is X-ray fundamental of X-ray absorption fine structure. So X-ray absorption fine structure is the X-ray is here. This is your sample, but the X-ray choose element of your sample. So, for example, you choose nickel sample or titanium in your sample, and next to your titanium, maybe oxygen exists near to your titanium. This is atom. So titanium atom and oxygen atom. And X-ray is injected. X-ray absorb, titanium absorb X-ray, electron, titanium electron. For example, which electron? Depending on energy, but titanium 1s electron, K electron is propagate, travels towards your oxygen atom neighboring to your titanium. Or maybe the other titanium atom, maybe around here, titanium, oxygen, titanium, it may travel to neighboring titanium atom, electron, 1s electron travels. And that is scattered back like X-ray diffraction. This is electron, but the diffraction always happens. So, and by this ongoing and traveled back electron, it's, sorry, this is Japanese. I use this, maybe in China, they can read Chinese characters, so sorry for this point. It interferes, and then this type of structure. So this is X-ray absorption, but this is the interference. And you see this not flat picture, this kind of the oscillation is obtained. This is the X-ray absorption fine structure. This is X-ray absorption here. This is depending on energy, but this kind of the oscillation, this is fine structure. So fine structure, in other words, fine structure is the information what element exists at what interval. And this kind of interference overlaps. And so it is analyzed, and how many oxygen you have seen from your titanium sample, how many oxygen atoms exist, and how many titanium atoms next to oxygen exist. That is analyzed. That's important information to analyze photocatalysis, like my example today. Time is coming. This is energy is changing, and X-ray absorption near each structure and X-ray absorption extended longer range absorption data structure. So this is you obtain variance. So for example, charge, titanium charge was 3 or something like that, 3 plus, reduced from 4 plus by at the end of photocatalysis. Such information is given, and extended X-ray absorption structure, the titanium coordination number was 5.5, somewhat due to somewhat reduced reason. So this information is given. Zanes and x-axis obtained. And this is, I skipped this. This is theory, a plane wave approximation theory. So you obtain the coordination number distance. This is Debye-Wara factor. This is vibration factor. So by vibration, the amplitude becomes weaker. This is, see this minus sign before exponential. And so this is what was measured. Maybe also if you wish to do such, it may be helpful to show this. X-ray is, this is the exit window of, this is hidden, but you cannot see the here, but here there is the open window, and this is exit of the vacuum from the synchrotron, and helium is filled inside, and X-ray is coming from this red line. So this is detector of filled with, in this case, for example, nitrogen gas. Nitrogen gas here, there is electrode charged with the 500 volts or 8,000 volts charge, and nitrogen is ionized, and we detect the current between these and see how much electron the penetrate is calculated. The X-ray ionized nitrogen in this charged field. And this is sample, and this light is for photocatalysis. So UV visible light is irradiated to, and this glass is filled with the CO2 and hydrogen or CO2 and moisture to proceed photocatalysis. So, and then this is, it's too bright and we cannot see sample itself, but the X-ray penetrate the sample and this is detected. So how much X-ray is absorbed here is calculated by monitoring the other ion chamber here. So maybe time is coming, but this is one of the, this is somewhat too, but this is our own technique to show. This is the, for example, silver bond length is here, but this amplitude is related to silver. Basically, how much silver is around your silver. So silver nanoparticle size is reflecting silver nanoparticle size, but also somewhat more the advanced technique is used here. Maybe I do not talk everything, and it's somewhat complicated, but very, very interesting because this vibration factor is associated with the coordination number. Coordination number is here. So coordination number slight increase means very slight increase of silver nanoparticle size growth during photocatalysis observed, but this vibration increase is much more evident, clear. So based on this vibration, we can calculate based on this theory. The correlated Debye model is based on this. This thermal factor and temperature correlation is given for bulk site silver and surface site silver. Because this is silver nanoparticle, so surface site is the silver site. Must be considered because about half is silver is at surface. So temperature is different because at surface silver it's easy to move because it's less silver around you at surface silver for surface silver. So based on these two correlation, we can obtain the silver mean temperature of the silver nanoparticle. So it grows, but light is off, drop down very, very quickly. So this shows by UV visible light, maybe like surface plasma resonance I showed in UV visible absorption characterization spectrum. So due to this absorption, light energy transforms into heat, and silver is heated up to 392 Kelvin. And due to this effect, photocatalysis takes place. That was found. So using technique, everything, the monitoring these reaction step was not talked. Such characterization, reaction mechanism is considered, but time reason I do not talk. And I say something, 2 points, and finalize today's characterization talk. One is this is nickel catalyst forming methane using GCMS. And yeah, like yesterday, I was comment and so this is FTIR. Yesterday, the IR ATR setup was, and we use the transmission setup. And so this is FTIR magnified picture. And so this is which was detector is this side. So light source is here, infrared light source. And this is sample maybe as disk. And this is the light fiber. And so sample is irradiated by the UV visible light, and detector is here, so avoid, because it contains also infrared. A part infrared light is, so avoid this excitation light penetrate into this detector. So direction is determined. And so, and inside this CO2, this is connected to vacuum, as I showed before. This one. Here. Here. So this is vacuum, and here pump. Pump cannot be seen. Below this, the pump. If this 2 or 3 pump is here, vacuum pump. And so connected to this vacuum system, this is pumped, and also to thin CO2 is introduced, for example. And so, and inside this, the photocatalysis is taking place, and the surface species on this, the sample disk, is measured. And so, like this, whatever the setup, the absorbance is obtained, whether you use IR, ATR, or IR diffuse reflectance, it depends. So maybe time resolved study may be also interesting, I think. And so here, choose a region, FTIR, as everyone is using in some way. But for our case, the methyl and methyl species, well, this is formate, CH stretching region. And also here, region. Oh, no. This is CO stretching region, stretching vibration region. All region carefully checked, and depending on the condition of your reaction, because it's connected directly to CO2, hydrogen or water reaction, and also UV visible light for excitation. This is COO. So asymmetric and symmetric vibration section for carbonate, but also bicarbonate. So check by seeing this, I stopped very, very soon. And because this is a request from yesterday, so I wish to include the FTIR results. So by utilizing this, we assume the reaction mechanism. And reaction mechanism like this one. So for example, CO2 bicarbonate based on FTIR, and stronger absorption based on the exchange reaction to thin CO2 exchange reaction using the mass spectrometry. And the silver temperature was warm. That was found based on the analysis of the EXAFS, the analysis using synchrotron. So hydrogen spilled over, and then the couple with the strongly absorbed bicarbonate to form CO. We assume so, and it was published and well read, but we continue, and this is still not drawing, or we need more effort is needed. So it's ongoing, and this is the not published. This is reviewed, and this is now we are revising we are revising this until November. The review based on reviews. These 3 lectures I would not have time to introduce our members. Unfortunately due to time reason. But I introduced the Diana-san and Anita-san in laboratory also. I hope on October 26th many, but not all the audience. That cannot come to my laboratory, but I'm looking forward to seeing the seven friends also on October 26th. And this is the DFT calculation result, our calculation, and this is the under division based on review comments to the Journal of the Physical. I believe this can be published if everyone work hard and answer all the comments to reviewers. So, but still here it says many things and before revision. The CO2 absorbs like this type, the M shape was found at the oxygen vacancy site. The exchange reaction and CO2 absorption, strong CO2 absorption took place on oxygen vacancy site. And hydrogen comes, and this route, this square OCOH species, and forming CO by filling oxygen vacancy by hydroxy, and create the original structure, but not making vacant oxygen vacancy. Rather than that, CO2 directly absorbed again, substitutes in the H2O formation, and oxygen vacancy is recreated. This calculation is, today's talk is characterization, but the calculation, we are forced to need to do this because this kind of intermediate structure, it's very, very difficult to find by FTIR. So further, we continue study, maybe time result study, and also advanced calculation study depending on time. Time-dependent study is needed. So talk is not very, very straightforward, and many things is mixed up, but this is the end of the talk. Thank you, Diana-san.
Thank you, Sensei. Okay, thank you, Sensei. It's a nice presentation, especially for the characterization of material like FTIR, and then also JAPS and other measurement. Okay, now continues to the second speaker. I think Dr. Indah, are you ready?
Okay, thank you very much, Dr. Diana.
Yes,
Okay,
please.
maybe first I want to share my presentation first. Okay, so can you see my presentation already?
Yes, clear.
Okay, okay.
Maybe not yet slideshow.
Okay,
Dr.
okay.
Indah.
Okay, I'll slide so. Okay. First, maybe thank you very much to Dr. Diana that have given me the opportunity to give a talk in this world-class professor. And maybe I would thanks also to the Pajajaran University who who gave me an opportunity to collaborate with this institute or department. And maybe before I would say hello to Professor Izumi. Okay, maybe we haven't met before, but yeah, maybe someday we can meet because our research is connected, and also I also work on the photocatalyst project.
Great.
Okay, and before I would like to introduce myself. My name is Indah Primadona. I'm from Research Center for Advanced Material, National Research and Innovation Agency. Maybe some of you haven't know about this institution because this institution is just it's just delivered last year, September 2021. So 4 big research institute in Indonesia combined together become a National Research and Innovation Agency. Before I worked for Indonesia Institute of Sciences, but my office is still in Bandung, Cisitu. You can see here, this is my office is still under construction. Maybe this year will be finished, and hopefully we will have some of a new instrumentation and new laboratory. So I hope we can get more instrument to characterize, especially for characterize material. So in this talk, I would limit my presentation, or I would limit my talk about the structural and morphological analysis of zinc oxide superstructure. So before go to the main topic is about the characterization of the material, I would like maybe introduce to you about the classification of the nanostructure material. So you have actually because most of people attend here is the students, so you can get a picture about what kind of material I would like to characterize in the next slide. So there are actually the nanostructure material classified become 4 in general. There's 0-dimensional, 1-dimensional, 2, and 3-dimensional. So for 0-dimensional is material is relatively very small, is usually less than 10 nanometer. So it's like a quantum dot, a semiconductor quantum dot, or carbon quantum dot, or other matter dot. And for 1-dimensional, it's like only one direction is longer than other directions. So it's like nanorod, nanowire, or nanotube. So one of the direction have a diameter very small, is less than 100 nanometer, but other direction or one, but another direction have a length maybe about more than 100 nanometer, even micrometer. And 2-dimensional is like here like a sheet or films. So there are 2 direction. The size is comparable, but the other direction is very small. It's like here. And how about the 3-dimensional? So all of the direction X, Y, or also Z direction have a comparable size. So usually less than 100 nanometer or even micro. So let's go to the what I'm going to share in the next slides is the superstructure. So in this work, actually, I would like to share my experience. Actually, here I just want to share about my research experience is actually this is a complement with Professor Izumi talk. So Professor Izumi talk is more on the basic. So he introduced about the basic or the principle of the characterization. But here I luckily so it's not like I prepare my slide is not about the basic principle of the characterization. So this is about my experience how to characterize the nanomaterial that we synthesize. So before go to the characterization of the superstructure, maybe better you also understand about what is the superstructure. So the superstructure is basically three-dimensional nano or microstructure which arise at the expense of one-dimensional and two-dimensional nanostructure with control morphology and orientation. So you can see here, this is like nanorod. This is a one-dimensional nanomaterial. So if we add a growth modifier in the synthesis reaction, this nanorod will grow together with other nanorod and build the assembly like this. So they stick together, but with the control morphology and orientation. So to produce or to generate like this structure, it's like bigger structure but contain a lot of nanorod inside. So it's like a nanoflower. And also here you can see in the figure E, like a nanoseed. Nanoseed can combine together to produce a microsphere here like this, but it's usually for the superstructure, the microsphere generated is microporous because it's combining from many one-dimensional or two-dimensional structure. And so what is the advantages of the superstructure? The superstructure material compared to the 1D or 2D nanostructure. So usually, generally, it have a good crystallinity and conductivity, and of course, high surface area and also like active sites like this. And according to the theory and also experimental result that the material dimension, of course, affect the physical and chemical properties and will lead also affect to the further application. Like here, this Zimosa nanoseries two-dimensional nanomaterial. In this figure is they combine together to produce a three-dimensional or superstructure like nanoflower and also needle flowers. And you can see here, of course, this will affect the optical properties like absorbance and also the reflectance and also emission properties, and will affect the photocatalytic properties. You can see here that when we use a nanoseed, the blue line here, the reduction of the catalytic properties is quite slow. But when you applied thin needle flowers or the seed flower, you can see the green and the red and also the black line here. The catalytic performance is become getting better. And you also can see here when we use nanosphere, compare with the like a nanoflower or also nanorod. You can see here that the oxide flaky nanoflower give a highest percent degradation compared with the zinc oxide nanosphere and zinc oxide nanorod. Although the diameter of the zinc oxide nanorod and also nanosphere is smaller than the zinc oxide flaky nanoflowers, but in this paper they said that the active site is bigger. The zinc oxide flaky nanoflower have an active site, exposed active site is bigger than others. So now you already have a picture about the what is the one-dimensional, two-dimensional, three-dimensional, and superstructure, and how they dimension affect the physical and chemical properties, and also of course also affect or also affect to the further application. And now I will go to the main topic to our talk is about how to characterize the morphology of nanomaterial, to characterize the material that we synthesize. So here I will not talk about the instrument that we don't have. Of course, in Indonesia, in Indonesia, it's not like in Japan. So many instruments in Japan or sophisticated instrument they have, but in Indonesia we have a limitation. So what I wanna push here is what we can do in Indonesia with our instrument, but we can generate information based on that. I think enough information is for the publication in the Q2 or even in the Q1. As long as your novelty is very good. So here, the structure and morphology analysis provide a full overview throughout the crystalline and also morphology structure of material, as well as information about the surface. So here, for the morphology analysis, it's about the how big the material you synthesize, and if it is a film, how thick, and what is the shape of our material, our synthesis material. So it's including in the morphology analysis. And usually it can be characterized by SEM and also TEM. And how about the crystalline structure? Because this is of course this is the important part of the characterization of our material. Because once you synthesize, you have to know about the crystal structure of your synthesis material, your prepared material. So about the structure or phase and crystallinity, crystalline size, and crystal orientation. And it can be done by XRD, X-ray diffraction analysis, X-ray diffraction. And how about the surface functionalization? If you coat or if you coat your material with like some organic material, you functionalize for other application. Yeah, actually you can characterize in Indonesia using FTIR. Of course, this is XPS. Actually, XPS is the best instrument that can analyze the surface functionalization. But Indonesia we don't have. But actually, in our institute, maybe next year, we will buy XPS. So hopefully in the future, I can introduce to you about the XPS instrument, and we can use together. So here, how to characterize the one-dimensional zinc oxide, because I synthesize, I prepare zinc oxide, so I will. This is actually can be used for other material, but what I'm more focused is here is one-dimensional. And by electron microscope. So here there's a zinc oxide nanorod, zinc oxide nanowire, and zinc oxide nanotube. Once you synthesize, once you prepare material, for example, you synthesize, you follow a procedure to synthesize the nanorod, nanowire, or nanotube. What you can do is, in the beginning, is using a SEM. Yeah, of course, you can see here. Yeah, there's a zinc oxide nanorod is successfully prepared, and also nanowire and nanotube here. And you also can you can process your data, or you can calculate the average diameter of your zinc oxide nanorod, nanowire, or nanotube using the image software. So here, the average, you can see here the average of the nanorod is 151 nanometer. Nanowire is shorter or smaller than nanorod is 60 nanometer, and the nanotube here 157 nanometer. You can see here the nanotube, there is a hole here. But if you want to further detail or further see how deep the hole of the nanotube, you have to analyze further using the DEM. You can see here the deep is, you can measure. And if you want to see the length or the height of the one-dimensional nanomaterial that you prepare, you can utilize the cross-sectional SEM. So here you can also analyze the average height of the nanorod, nanowire, nanotube using the image software. And after you characterize using SEM, you can go further to the XRD to know the structure of our prepared material. So in this instrument, or using this X-ray diffraction pattern, you can see the fingerprint that lets you figure out what is in your sample. So first, you have to generate the XRD spectrum, and then you compare with reference pattern to determine what cases are present. Using there is so many software to analyze this. For example, using Diffract-EVA, Match, HiScore, and etc. And of course, inside has to have a database. Like here, we have a PDF database. So you analyze your XRD spectrum in this software, and you have to in that software, it will generate so many database, and you can pick up, or you can pick up the highest score of the database with which is the highest match with our spectrum, XRD spectrum. See here, and we can from that we can annotate our peak. This is the HKL, or the lattice parameter of the our sample. And according to this result, we can get the crystal structure of our sample. The crystal structure is hexagonal wordite, and the highest peak here is different with the different with the database. The highest peak here is 002. So actually the difference of the intensity here is depend on the morphology of our material. So because of our material is one dimensional, so probably only one direction of the plane is is the more than maybe the volume fraction of the major quantity of our prepare material is only in one direction. Probably it may be 101 or 002, but here you can see very clearly is in 002 plane. So you can see here that this is the zinc oxide hexagonal unit cell. 002 is in this plane, and 100 is in the trunk of the nanorod, and 101 is in this plane. So it is very obvious that if our nanomaterial is one dimensional nanostructure, the major plane observed is 002 here. So it's perpendicular to the glass substrate. So it is actually in agreement with the SEM result. You see here, the SEM result is a perpendicular on the glass substrate. So here, the XRD spectra also support the data. But if you compare with if you make a comparison with the nanotube, nanowire, and nanorod, we cannot see clearly actually which one is longer. Of course, using SEM, we can see, we can measure. Using SEM, we can measure who is the longest. Here is the longest is the nanotube. The second is the nanorod, and the third is the nanowire. But here we can not see clearly. So using this the formula. But before that, I want to introduce about this formula. Actually, this one is the Harris texture coefficient. So actually, generally you can measure the height in using the SEM, but using the XRD also we can predict actually which one is the longer than others. But we cannot measure exact height of the one-dimensional nanomaterial is only a comparable. So single factor that affect the diffraction intensity is the crystal preferential orientation. So this one is the about the preferential orientation. So Harris texture coefficient was determined quantitatively to estimate the degree of preferred orientation. So we can predict or we can compare the height of the one-dimensional nanometer using this Harris texture coefficient. And the formula is like this. here is n is the total number of diffraction peak considered in the evaluation. So we have to pick up which peak can be, which peak will be included in the in this calculation, and how many peaks. And this one is the intensity, the measure relative intensity of the peak corresponding to the HKL diffraction, and IR is the relative intensity from the same diffraction in the standard powder sample. And also the crystalline volume oriented along each HKL also influence the XRD peak intensity. So this is the formula of the volume oriented along each HKL. So according to this spectrum, XRD spectrum, so I calculate the TC and also V HKL. So you can see here that the TC, this is a preferential orientation. So I pick up three peak to be considered in this calculation. Is three highest peak is 100, 101, and also 002. So here the TC value of the TC value is the black line here. So you can see here that the nanotube for 002 nanotube is at nanowire is comparable actually with the nanotube, a little bit higher for nanowire, and the lowest one is the nanorod. So this is the in agreement with the SEM result. And also the volume also is the same for 002. Also the same. The volume of the nanowire for 002 plane is also the highest one compared with the 100 and 101. So this is I just want to show it to you with this formula that we also can predict if you want to compare the preferential orientation of our crystal of our several materials. You also can use this formula or this and now we go to the zinc oxide superstructure. So, but before I go to the characterization part, so this is the I want to show you the little bit how to synthesize the zinc oxide superstructure. Yeah, and here we also beside we synthesize a composite form of the zinc oxide superstructure. So we composite the zinc oxide superstructure with the carbon quantum dot. So the carbon quantum dot, first we synthesize the carbon quantum dot with different starting material. So we use ascorbic acid, and for the end of carbon quantum dot we add a urea. But for the NS, nitrogen sulfur dope carbon quantum dot, we use cyurea as a starting material, and then we synthesize using a hydrothermal method, and here, and then after that we mix with the zinc oxide seed on a glass substrate first. So first we have to make a zinc oxide seed on the glass substrate, and then we mix with the carbon quantum dot and also zinc oxide precursor, other zinc oxide precursor, and then heat it using a hydrothermal method, and finally we can get the composite here. So after we synthesize, first what we want to see is the of course the morphology and also the crystal structure, whether our zinc oxide can be synthesized or is successfully synthesized or not. So here, after we synthesize, what we did first is the Sem analysis. So here, what we get is for the zinc oxide and the carbon quantum dot, we got the nanoflowers form, and for the Sn dot carbon quantum dot, we get the hierarchical microsphere like this. So actually, using this SEM image is enough, but maybe if we want to have a clear image, maybe we can use FASEM. So again, the same with the one-dimensional nanostructure. We analyze we calculate the average of size using the image here, because we synthesize in a composite one. So I go further to the Eds experiment to know what elements in our material. So after the Eds experiment, you can see we can get the of course there's a zinc element and oxygen and also carbon. And I don't know why here because the carbon quantum dot is contain the organic element. It's like a carbon, oxygen, hydrogen, and also nitrogen, because here we add some urea here. But of course, the hydrogen cannot be analyzed by ADS, it's too small. But nitrogen, I don't know why we cannot be detected here. The nitrogen, maybe the concentration also is very small. But here we can also differentiate with this. What we add here is the urea, so it must contain the sulfur here. Yes, this is actually okay. The EDS result contain the sulfur here is about 2.28%. So, but the nitrogen also cannot be detected here. So actually, we can distinguish these two material using the EDS. And after that, we go for the analysis to the XRD. You can see here the composite one here. Again, we also use EVA to analyze or to see the crystal structure of our material. We match with the database, and we get the hexagonal woodsheet in those two prepare superstructure. And here you can see the highest peak is not 002 like in what we observe in the one-dimensional nanostructure, but we observe 101, the highest peak. So the preferred orientation of this in this prepared material is in the 101 direction here. And also you can see here, because our material is a composite one, so you can see it's not really sharp. Not really sharp. And also there's a hum here, so it means that there is an amorph. So you can see the crystallinity is not so good actually, especially in the nitrogen dope is about 37.5%, but for the SN dope is 61.1%. It's not like a previous 1D nanostructure. As I remember, the crystallinity is about 90%. The same, we also calculate the TC and also VHKL. Here, the preferred orientation is 101 direction. And now, because what we synthesize is the composite one, so there is an organic contained in the material. So we analyze our material using the FTIR. to see whether the organic layer or organic layer is contained or is exists in our material. So you can see here, this is the the purple one is the carbon quantum dot, end of carbon quantum dot, and the green one is the SN dot, carbon quantum dot, which is generated from the thiourea here, and the blue one is the zinc oxide, pristine zinc oxide. The black one is the zinc oxide composite with the N dot carbon quantum dot, and this one is NS dot quantum dot with zinc oxide. You can see here that there is you can see here there is a difference. You can differentiate between these two, the black one and the orange one. The peak in about at about 2000. Here 2000. This is characterized for the NCS functional group is observed in the our NS composite here, because in this the green spectrum also exists. So, and for the end of carbon quantum dot zinc oxide, the black one here, the NO nitrogen oxygen stretching exists. The same with the purple, the same that we observe in the purple spectrum. So we can conclude that using the FIR, we can also observe that N dot and S dot is carbon quantum dot is successfully functionalized on the zinc oxide material. So for the photocatalysis purpose, we further characterize those two materials, the absorbance and also the reflectance using their UV visible spectrophotometry, and from that we can calculate the band gap of our material. Okay, because in this actually for the absorbance UV or visible, we measure in these two range, in the UV in the UV region and also in the visible range. This is because for the photocatalysis we have to synthesize, or we have to prepare the material with a certain purpose. For example, that if we want to use a UV light to in the photocatalytic application, so our material, our prepared material, have to have a high absorbency in the UV range. But if we want to use visible light in the photocatalytic application, we have to prepare a material with which is have good absorbance in the visible range. So, this is the and for sorry, this is still Indonesia word. So for the photocatalysis application, we also need to measure the photoelectrochemical properties of our material. So this is the system that we built for the photoelectrochemical measurement. So this is the system or container that we put the photoanode or working electrode here, and we put in the box, because we want to we want to irradiate with whether UV light or the visible light here, and connected and this system connected to the other system which contain the reference electrode, and this is the potential stat instrument, and we experiment or we run the experiment about the linear sweep voltammetry and also corona amperometry to know the performance of the photocurrent that generated by our material. So this is the result. The linear sweep voltammetry that we use first in the the black one is in the light off condition, and the orange one is the light on condition. You can see here that using the if we irradiate with the UV light, that the photocurrent can be generated in the very low potential. So meaning that our material is the photo assisted or the photocatalyst material, the active photocatalyst material. So, and after that we did the we did the corona amperometry to see the how much the photocurrent can be generated using the, as I remember, this one is without voltage. Without applying the voltage, we can still see the photocurrent if we applied if our material be irradiated by the UV light here. So according to this result, that our material is a potential photocatalyst material. So other zinc oxide superstructure also be synthesized, also be prepared in our lab using this the composite of the composite material, also prepared in our lab using this method. Before we prepare the composite is using like one pot, so actually we don't know where is our how the organic compound in our material. It's like mixed together or in the surface of the zinc oxide nanosheet or nanorod. We don't know, but here we also prepare. Beside that, we prepare using the LBL method, like this paper. We first synthesize zinc oxide, nanowire or nanotube, and then we functionalize the carbon quantum dot using this method. So you can see here we can analyze this using the SEM, but you can see here the TEM image. You can see where the carbon quantum dot position in our prepare one dimension nanomaterial. You can see the black dot here is the carbon quantum dot or organic material here. So here that we synthesize successfully the nanopencil, and we analyze using SEM. And then actually we also carry out the LBL experiment, but because we don't have the TEM, so we run the EDS mapping. You can see here that based on the EDS data, the zinc oxide, oxygen, carbon, sulfur, and also nitrogen here is present in the surface of the zinc oxide nanopencil. So it's a uniform distribution. But of course, if we want to know how they carbon quantum dot distribute on the nanopencil, of course we have to do the TEM experiment like this. And the same, we want to know we want to know whether the carbon quantum dot exists on the surface of our zinc oxide. We also do FTIR experiment was carried out. You can see here that this one is pristine zinc oxide, and this one is the pure quantum dot with carbon quantum dot we prepare. You can see here that this one is the composite one, so contain the peak belong to both zinc oxide and also the SN carbon quantum dot. So meaning that in the composite one we prepare zinc oxide composite, graphene quantum dot or carbon quantum dot successfully. The same in XRD also. We carry out the XRD experiment to know the crystal structure and also the crystallinity of our sample. Okay, maybe that's all my presentation. That's all my presentation. So if maybe there is a further question, but before that, maybe I'll give this time to the moderator, Dr. Diana. Thank you very much.
Thank you, Dr. Indah, for nice presentation. I think completely. First, Professor Ijumi about the fundamental for characterization material, and then continue from Dr. Indah for application, especially for zinc oxide. Now I invite from audience for discussion, but I think the time is limited. I'm sorry, maybe just one or two questions. Yes, please. Any question? Maybe the topic this lecture is very complete and then clear and understand also, but Dr. Ina talk about in my country, also maybe next my student also will give some question. Dr. Indah said that in our country also we have unlimited measurement, but I saw from Dr. Indah data is very nice, and then also complete for data. Maybe Dr. Indah also can submit to the reputation paper, maybe quartile 1 and also quartile 2. Maybe Dr. Indah, I want to know, to ask about this result. This is belong to Anissa and another Anissa, not Anissa Lutfia. Anissa and Afifah data, or also Rifki Adia data?
Yeah, actually this data is belong to our collaboration. I compile Anissa, Afifah, and also Rifki data. So hopefully it can we can finish the paper soon, and we can submit after we finish writing. Due to the instrument limitation, like I said, so to add more value of our paper, so we have to cite more paper, and also we have to study deeply. Maybe we have to refer to other paper to explain our result. Yeah.
Okay, thank you, Dr. Indah. Okay, here Ibu Dr. Yusi Dewati, raise hand. Yes, please open mic.
Yes. Thank you, Dr. Diana. Thank you for a very nice presentation from Professor Izumi and Ibu Indah, PhD. Really interesting about both research. I want to ask about here as Ibu Indah said that we have a limitation in analysis method. Also we don't have like exact if as we don't have that. And my research about find a new compound, especially coordination compounds, metal complexes. We have to find a new structure, a new single crystal structure generally, and we almost have difficulties about the analysis because no the instrument here in Indonesia, and then about the preparation of the sample. I think we should graph the single crystal first, to find the structural geometry. I want to ask to Professor Izumi, according to the same source that used X-ray, in EXAFS, is it possible for us to get a new structural geometry of any compound from EXAFS, or just like the single crystal XRD do? Is it possible to find a new structural geometry? And then how about the preparation of the sample? Is it easier, or we should do the same graph single crystal, for example? That's for Professor Izumi. And then for Ibu Indah, very nice picture, very nice picture from scanning electron microscope, or TEM, I think, and then the nanostructure also, in the field of bioinorganic, is it is it important, for us to make our compound to be nanostructure, to implement for example, for drug delivery in the body, for example, yeah, is it important or necessary? What's your opinion of for that? Thank you. Thank you, Bu Diana.
Okay, thank you very much, Dr. Yusi Dewati, for the question. Please, Izumi Sensei, maybe you can answer.
The question, do you wish to analyze single crystal, your crystal? The X-ray, the crystal structure analysis, do you wish to perform?
Yeah, I wish to find a new structure.
Crystal structure?
From new compound, for example, new metal complexes.
Complexes.
With new ligand.
Metal complex. You have metal complex crystal and synthesized crystal, and do you wish to analyze that?
Yeah, I want to know the structural geometry.
Crystal structure geometry. I think the synchrotron may be good, but also you use the crystal structure analysis apparatus rather than synchrotron. Synchrotron crystal structure analysis is also possible, but I suppose I do not know detail your sample, but I suppose you use these single crystals structure analysis, not simple X-ray diffraction, the apparatus. You use the single crystal, the crystal structure analysis apparatus is possibly nice for you, I suppose so. It depends on your sample. And so you choose the appropriate, the analysis, so how to say that? So that is also important to, so you will find, maybe it's not available in your laboratory, you use common one in Indonesia or in other facility in Indonesia would be, I think that is done. And also some kind of rare the analysis technique, like I introduced the synchrotron analysis today. That may be somewhat rare and not something like a little specific. For such case, maybe if you do not have like Diana-san, the collaboration, such program, maybe utilize between Indonesia to Taiwan, as the Inda-san's talk, or so such collaboration may be also done, I think. So if you supply a little detail for your sample, I can tell you later.
Okay. Thank you, Prof. Izumi. Yeah. So we should better use X-ray single crystal to find a new structure.
I think you have somewhere if not in your laboratory, you have in Indonesia you have apparatus. I think so.
Yeah, but not operating yet, I think. Yeah. Yeah, maybe next next week can explore with that instrument. Yeah, thank you very much, Prof. Izumi. Maybe I will contact you if I need to analyze my sample. Thank you.
Okay, thank you, Sensei. Now, please, Dr. Rinda, to answer.
Okay, thank you very much, Dr. Yusi. Yeah, of course. So as far as I know, for the biomedical application, especially if you want to enter the material to your body, it better you make a homogeneous nanomaterial. So have the not only the size has to be nanomaterial, but also homogeneous. So it can be entered to the for drug delivery, it has to enter the blood vessel, right? So if you have a homogeneous material, it can be easily to enter or to explore to your body. And you also can functionalize with the specific ligand on the surface of the material, so it can recognize the specific target to your organ in the body, actually, that you want to cure, actually. So as far as I know, like that. So that's why the nanotechnologies become more popular on the biomedical application. Yeah, maybe that's my answer, Dr. Diana or Dr. Yusi. Hopefully can answer your question.
Yes, clearly, Bu Indah. Thank you very much. Maybe later we can work together.
Yeah. Of course, actually, the material that I synthesize actually, I think can be also applied to the biomedical application. But because I haven't time or I haven't student yet to do that, so that's why we haven't explored for the biomedical application.
Okay. Yeah. Thank you very much.
Yeah.
Thank you, Dr. Indah, and then thank you also Dr. Yusi for question. The next question from Dr. Irwan Kurnia. Are you here?
Maybe I just
Hello, Dr.
want
Irwan. Okay, please.
Okay. Thank you, Dr. Diana, for the opportunity. Actually, I just want to say thank you very much to Professor Izumi for sharing the knowledge about the in situ FTIR, actually, because in the high impact of the paper, most of the paper is put the analysis of in situ FTIR for determine the mechanism, the reaction mechanism, and also sometimes is for distinguish the Bronsted and Lewis acid functionalization on the catalyst. So I would like to say thank you again to Professor Izumi. Okay, maybe it just want to say it.
Thank you. Thank you. You're welcome.
Okay, thank you, Dr. Irwan. Any question? Oh, this is from my student, I think, Sensei. Can you read in the chat box?
Oh, chat box. Okay. Oh. Let's see if we can improve it. See to calculate what was my sample. So if you do not, you can read this in the second question. Is there any category sustainability? Okay. For my part, Diana-san bring.
Yes.
Bring the sample.
Yes, Sensei. Maybe I have many, maybe around 20 more. I think sample. This is belong to my student and master degree undergraduate, and also PhD student, and they send me a sample, and may I measurement in your lab, of course, especially maybe also for catalytic activity. Because in my lab we don't have gas reaction, only liquid reaction like dyes and some of organic compound, for example, phenol, but we don't have a reactor for gas reaction like in your screen. So maybe I want to do with Anissa Chang also. Next in your lab, we want to take reaction gas for our sample, especially for photocatalysis sample. Is this right?
Yeah. Talk about in detail, and we proceed and check, see which one was, for example, looks good or not.
Yes.
Yeah.
Thank you very much. Okay, the next question from Lintang for Dr. Indah. Dr. Indah, can
okay, thank you. Okay, thank you very much, Lintang. So, what your question is about the composite. Which one is better, right? To make it together, for example, like precursor, directly mix with the organic compound and then mix together to make a composite, or we make the material first separately and then mix together, right? So actually, it's depend on the application, I think, because there is an advantage and disadvantage of about that. What we observe is if we put together like precursor and also the what's the organic compound together, and then what we observe is the crystallinity is going down. But of course the process is faster. The process is faster, but the crystallinity is going down. So if your application need to have a high crystallinity, so better you make separately, like zinc oxide separately, and then also the precursor, the organic layer, and then after that you combine together, so it can like become a layer on the surface of your zinc oxide or inorganic material. Yeah, I think that is my answer. Yeah, but okay, but if you put the organic material put together with the precursor, you can actually you can generate different types of the morphology. Because the organic material here also role as act as a growth modifier. So that's why it's depend. I cannot say which one is better, but it's depend on the application what you want to pursue. Yeah, I think that's my answer, Dr. Diana.
Okay, thank you very much, Dr. Indah, and also Professor Izumi. I think time is over because in Japan now 12:20. Also, Professor Izumi. Now you have a lunch break, and then maybe Dr. Indah also you should continue to another activity. Okay, thank you very much, Izumi Sensei and Dr. Indah. Before we close, I have some certificate appreciate from our dean. Wait a moment. Yes, first this one for wait, it's going. Yes, this one yesterday talk.
No, yesterday.
Professor Izumi. Yes,
No.
Thank you very much. Guest lecture yesterday, and then also this one for today lecture. No. Thank you very much. And then the last for Dr. Indah. Thank you very much for lecture today.
Thank you very much, Dr. Diana.
Yes, you're welcome. Now, for the last, we want to take a picture. May all participants on your camera, please. Okay, wait a moment. Slide 1. 1, 2, 3, cheese. Slide 2. 1, 2, 3, cheese. Okay, finish. Thank you very much again, Professor Izumi, Dr. Indah, also all participants, Professor Ati. Hello. Thank you very much for joining this lecture. Also, all my friend from Universitas Pajajaran, from BRIN, also from Universitas Jambi, Wastu Kencana, Politeknik Bandung, and from other university. Thank you very much, Sensei. Maybe see you next week in Japan.
Yeah.
I hope.
A nice trip to Tokyo.
Thank you very much, guys. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi
Waalaikumsalam
wabarakatuh.
warahmatullahi
Thank you very
wabarakatuh.
much.
Okay, bye bye.
Bye.
Yeah.